Hello, everyone. Thanks a lot for coming by and joining this session. My name is Sean Park, and what this session is winning the online banking war. Let me just briefly introduce myself. I used to work for one of the big four banks in Australia as an information security consultant. And one of the biggest achievements I made in the bank was to create a online banking malware detection system without installing anything on the client's machine. And this talk is a little about that, and it is an extension of that one. But at the same time, I want to emphasize the fact that this talk has got nothing to do with any specific bank or a vendor. So yeah, please be aware of that. Also, I used to work for a few of those antivirus companies out there, and I am with Trend Micro at the moment. So, yeah. So in the past, we used to talk about the battle between the bad guys and the good guys in terms of the online banking malware from the perspective of anti-malware solutions. But in this talk, the focus is the battle between the attackers and the banks. So we're gonna have a look into the crux of the battle first, and we're going to set a strategic framework on that using a POC, which I have implemented, something called a MIPS. So yeah, let's have a look at that now. By the way, I do have to apologize for my voice. I caught a bit of cold, so yeah, so I do apologize for that, for the voice. Hopefully it's not too bad for you guys to listen. So that picture illustrates a typical banking malware campaigns that you actually see on the papers, on the articles, or et cetera, et cetera. This is basically one campaign usually consists of spam emails, infection URLs, droppers, the actual banking malware, and CNC sites, which provides the configuration of the banking malware, which usually contains, the list of the target banks, the banking page URLs, and the injection scripts, and things like that. So in the past, people used to think about the battle as simply writing signatures for the malware binary files, or simply blocking the URLs that is in charge of the infection, or blocking the IP address of the spam servers, etc., etc. But but the new battle I'm going to be talking about in this talk is not that. Let me go through a few of those screenshots I took. So these are the ones that can give you guys a bit of an idea about what the banking malware is doing, and I'm pretty sure a lot of you guys are already aware of this sort of stuff. So I'm going to skim through each one of those screenshots very briefly. So this one is popped out at the sign-in page. So it simply steals your phone banking code and a date of birth to do more fraud in other channels. And also, when you have when you have a one-time password token embedded in your online banking, well, that sort of information can be stolen as well. And sometimes it says your online banking website is temporarily unavailable. So that simply gives them a bit of a time to buy for performing the fraud. And sometimes you can see some sort of a pop-up message saying, please wait, and it just takes a long time to complete. And what's happening in the background is this. So the green lines are the packets that actually do some communications between the infected machine and the CNCs, so that it can get some more instructions. In some cases, when the malware is doing the transaction injection, it will just require a bit of a social engineering in there, because that method of so when the user is equipped with a two-factor authentication methods, such as mobile phones, for example, and the user is not expecting a message, and if an injection happens, then it's going to be a very unusual thing for the user to receive. So and that's the reason why that sort of screen is going to be useful to allure the victim to enter the code. Yeah, so there are a few of those stuff like that. And I mean, the point here is that well, thank you very much. So the point here is that unlike the a typical malware out there, a banking malware requires a web application logic that should be embedded in the online banking sessions. So just a few months ago, someone at the Black Hat Asia has already presented about how the banks can detect that sort of injects. So I'm gonna just talk about that briefly first, and then I'm gonna just move on to my main topic. So here, injection is just a very simple thing. So it's simply a piece of JavaScript that will be embedded into the page. So in this example, we've got a sign-in button there, which will be associated with the event handler, which will then grab the information stored in the fields. So it's just inject is just as simple as that. And if it was embedded in the transaction page, then it's going to be a transaction injection or a manipulation. So how am I going to detect that? If some people just might be confused about the detection here, because so we are not talking about the anti-malware solutions here. We are not talking about the online banking server. We are talking about just normal users who is using just PCs, right? And in the PC, your PC is infected with a banking malware. And it's the PC that we want to actually do the detection on. So when you're accessing an online banking page, what's going to happen is the client will do the HTTPS GET request, and in return, the online banking server will return the HTTP GET a response, which will contain the actual online banking page. And what we can do in the bank is we can embed a special script, which I call a MIPS script on the left-hand side, and alongside with the online banking page, a MIPS will actually run at in the same page. And also on top of that, of course, we've got the actual malware inject in there. So what we can do is we simply scan the DOM and see, because the inject is essentially a piece of JavaScript as well. So what we can do is simply scan the DOM and see if there's any other script that is not supposed to be there in the page. So that's a very simple mechanism to do the detection, and it can be still very effective. Right. Also, at the same time, on the server side, we have to maintain the actual signatures, because it's also possible that a third-party web browser plugins can also inject stuff into the page. But anyway, it's also important actually to maintain the signatures on the server side to reduce the false positives. So, all right, fantastic. So we got the detection now, and the game is over. Is it really over? I don't think that's really over, and that's the reason why we have this talk. So, DOM stuff is a mechanism to hide the presence of injected malicious script. And how does it work? It's simply, it's very easy. Actually, so what the malware does is simply injects itself and removes its own script node, and the injects a function that is a part of the script will be still activated when the function is called. So, for example, if a DOM element it has an event handler associated with it, it can be still, the function will be still invoked even after the script node is removed. It's because of the way the JavaScript's garbage collector is working. So as long as we have a reference to a DOM element, the function will be still activated, and it still remain in the memory. And there are a few of those patterns that the attackers can use to use that technique. So yeah, let's have a look at each one of those one by one. First of all, it's simply install an event handler to a DOM element. For example, a button object, and it will still the function that is existing in the script will actually still be active because there is reference from the DOM element to the removed script, so the script will be still in the memory. And also the selector reference is just another thing which can be also used. So you just just maintain another reference from other script to the body or DOM elements, and that a script will still be active. And also in JavaScript, we've got something called closures, which is simply a function, and so the function inside a function with the parameters, which actually is active only in the local function scope. So even after the outer function is just removed, the whole thing here will be still active because the element which is passed as to the outer function will be associated with the function inside. So that way, the memory inject can remain in the memory. So in terms of defense, how can we detect all those hidden stuff? First of all, I think we have to have the capability to enumerate all the objects in the memory. And the easiest way to actually detect the a hidden script in this particular example is to use a few of those just functions out there to do the to scan the objects. So you can use on-click a function property, add event listener function to add an event. You can use jQuery stuff to register an event. So for each one of those techniques, you can actually get the list of all the functions. So yeah, I'm not going to go through each one of those. It's not that much interesting. So and once we have all the functions that we have enumerated, so how can we actually detect whether this particular function is hidden or not? Yeah, one of the ways to do that is to do the artifact analysis. So just have a look at some sort of artifacts that it may occur when the script is just hidden. So as part of my research, I have discovered an artifact where when an object, so the a function object that's associated with the particular event is removed, the string of the namespace property is just empty. So I think that's that could be one of the artifacts that you can use for detection. But at the same time, I think if you dig further, I'm pretty sure there will be some other artifacts as well. However, a robust way to do the detection is to scan the entire object space, get all the functions, and do the comparison with the whitelist that you will get in a clean session. So I think that's the best way to do it. Okay, and now let's have a look at the MIPS infiltration. So if you ever look at the attack scope, in one single page, you have got everything up and running all at the same time. So we've got the original online banking page, and also we got the malicious inject, and also we have a MIPS script. So all running at the same time. But the thing is, the bad guys have the privilege here because they can insert some arbitrary code into the MIPS, and also they can modify the code, tamper with the data, etc., etc. So it's something that we should be aware of, and because of that, this attack is possible. So assuming that we are scanning the DOM, and we just grab the scripts and do the calculation of the SHA-1 hashes for each one of the scripts, and send them back to the server for the, for the detection. So in the normal cases, if you are an attacker and you will actually see the packets there. So for example, so each time when you're doing the online banking, the attacker will actually see it will always sends out A, B, and C. It's just so each one of those is just a SHA-1 hash of each one of those scripts that is running in the page. So we got A, B, and C all the time, and the attacker will just realize, okay, this is something that will always happen, and so when the attacker is embedding its own script in there, and it sees it has got one more stuff at the end. So we've got A, B, C, and D. So the attacker figures that out, and so they simply block the original MIPS traffic, and instead replay the packets. So that's sort of a technique. It can be used to simply, to evade MIPS detection. And so, how can we defend ourselves against it? So it's getting pretty hot, so I'm going to just take off my shirt. Right, so this problem has been addressed a long time ago already. So if it's a replay attack, what we can do is simply use some technique called assaulting. So what that does is essentially the server returns a random number, which we call assault. And we use that assault to transform the values. So in this case, the SHA-1 hash values of the scripts will be the one that will be transformed into something. So because each packet is each time we are accessing the online banking page, it will get a new salt. So the attacker will actually see something like that. So it's not going to be the same value for each packet. It's going to be a K, Y, Q, T, X, A, etc. So that way we can avoid the replay attack. As I mentioned before, the whole MIPS code is open to the attacker. So it's kind of a kind of open source. So what the attackers can do is basically insert its own code between the functions that MIPS has. So in this example, what the attackers does is embed itself between hash function and the sort function. So it will actually receive a list of hashes of the scripts, and it will look into the script. Sorry, it will look into the lists and simply just removes the hash value that belongs to the malware inject. So that way it can simply or not being detected. So the attackers can either insert their own piece of code in between the MIPS code, or they can simply reverse engineer the entire MIPS code and do the simulation. So they simply just call and fill those MIPS functions as needed. At this point of time, let's have a look at what the attackers can do. What the attackers are not going to spend hours and hours or even days of time to do reverse engineering, just of the MIPS code. What they do initially is simply do the dynamic analysis. So they put some breakpoints here and there, and do the evaluation, and do a search on a few of those strings that MIPS code I might use, etc. So they are not spending a lot of time doing the reverse engineering, but instead it's more of a behavior analysis. So it's important it's really important to understand what the attackers can do or not, because otherwise we could probably spend a lot of time protecting something that's not really worth. So for example, some people believe that using the encryption will actually help here. But in fact, it doesn't help at all, because the information which is key and the encryption algorithm or decryption algorithm will be available not only to the MIPS code, but also to the attackers as well. So, that doesn't help at all. So, in summary, I mean, if you simply blindly, apply, all of those algorithms to protect your MIPS code, it may not work, because you have to, first understand what you're protecting, and then you can actually, apply the actual protection algorithms on top of it. So, what is it that we actually want to protect here? So, what we want to do here is to guarantee the code integrity. So, we want to make sure that our execution of MIPS code is not compromised. So, one of the ways to do it is to do the code integrity check. It's like that. So in this example, I'm using a couple of random numbers to transform the function bodies into something. So the lines just highlighted in blue are the lines that actually gets the CRC of the actual function source code, and combine those with the random number. So if you want to evade the integrity of the code, a check in that code, you have to insert some piece of code in there, or you have to call the entire function using your own function. So in either case, you're just modifying the code so that that sort of attempt will be picked up, because it will be changing the final value of the integrity check value there. So that's one of the ways that we can just check the integrity. And I'm pretty sure there will be other ways to do it, but the key point here is that it's important actually to do the code integrity check, and that's going to be the basis of the talk in the following slides. So it could be the MIPS, it could be it could be the library, or it could be the DOM API functions, or even the online banking applications that can be spoofed or tampered with. So it's important to actually to provide a security for each one of those components in this picture. All right. So I mean, can this code be broken? In other words, is there a way to actually make it look like your MIPS code is not it's compromised, but actually actually it is compromised? Yes, of course, it can be done, right? If you spend enough time to figure out how to do that, I'm pretty sure you can do that. So I mean, the point is that it doesn't matter how smart you are, your algorithm can be broken. It's not just RSA algorithm, right? So so how can we address this problem? So one of the most promising solutions to this is to do the randomization of the code. So it's not only one single version of the MIPS code that you have, but you just keep like thousands of those, so that it's going to be computationally infeasible for the attackers to reverse engineer all the code and rewrite just all the evasion code. So I think that's the way to go. And this is one of the implementations that we could possibly have. So essentially, you have each line of the code, which I call a basic block here on the left-hand side. And you just get the combination of it's combination of those codes and put those into a few of those steps, which will give you a randomized code. So for example, you can apply you can simply connect each one of those basic blocks through a function call or just inline or even exception handling code. Also, you can dynamically generate the code, for example, using eval, or you can simply use a static code if you want. And at the end of that, you can just apply all those metamorphic techniques. So yeah, that's one of the ways you can defend, and that's one of the a major motivation of my research. So it's randomization basically, because it's impossible. So as far as I know, there's no algorithm out there. When it's open sourced, it's impossible to guarantee the integrity of the code. And other thing that you might want to consider is something called opaque predicates. I guess I'm not going to go through that right now because I don't have that much time right now. So also the other thing that's is pretty important is something called a rootkit. So in the operating system world, it means simply a technique that allows the attackers to hide the presence of the objects that the attacker wants to hide. And it does that simply by hooking into API functions and tamper with the data. So it can be applied, the concept can be applied to the JavaScript world as well. So in this example, it simply hooks into a function and invokes the original function. And the return a value is looked through, and if it detects a JavaScript which is a part of the a malware inject, it will be removed. So that way it will just avoid the detection. So in terms of the rootkit, as part of the defense, you have to essentially look through all the functions that your MIPS code is using, and also find out all the dependent functions as well, and just ensure that all those functions are not compromised. And in terms of how are you going to do that? Well, I think there are a few ways to do it, but this is one of the ways that I have come up with. So essentially, what you do is you just embed an exception to a potentially a rootkitted function. So that a toString function here is it accepts only a function object, but if you pass on a string in there, it will trigger an exception, and on exception, if you have the opportunity to look at the call stack of it. So if you have a look at the stack of that, you can see that all the strings there, but in a clean session, that a red line will not appear, and that function was indeed rootkitted in this particular case. So a fraud analyst is something that you can do on the server side. So essentially, our bottom line here is that we should be able to see a message from the web browser to actually detect the presence of a malware inject. Yeah, but if we don't see anything, the whole thing will be just useless, right? So we should have the capability to ensure that if we are not seeing the information from the browser, that should be flagged as malicious. So that's what it is. And detecting moving targets. So inject is just like a normal software in a JavaScript, right? So each time the attackers are upgrading their code, it doesn't change much in many cases. So what we can do is we use the similarity hashing, such as TLSH. So what we do is we can see, if two injects are quite similar to each other, we can see that sort of stuff. And I'm going to give you a demo on that very soon. Zero knowledge proof is a very interesting technique. It was simply, in simple words, when two parties have a shared secret, if they can prove to each other that they do actually have a shared secret without transmitting the actual secret on the wire. So the reason why I'm just mentioning that here is because it can be a very useful technique in the MIPS code design. So well, there are a few ways to use that here, but I think the most important feature of that is MIPS hardening. So we've got a lot of information that will be transmitted from the web browser to the server, and a lot of them, can be, you know, a further secured by simply using ZKP. So that was the reason why I was just mentioning that here. So let me go through the demo. I will do as much as possible. Okay, with the transaction injection, what do we mean by that in the first place, right? So I'm gonna activate that piece of code. Okay, yeah, that's a payment page on the left-hand side. Alice has got $5,000 and Bob has got nothing at the moment. And we have got a money mule. It should be, well, it's not that one, sorry about that. Should be that one. Yeah, so that's a money mule, which has no money at the moment. So if I do that, if I make a payment to my friend Bob, and I'm paying $5,000 as a gift, right? So to pay now, paid, right? So it's paid to Bob, and Bob is supposed to receive something, but he hasn't received anything. Mule has received it. So yeah, so that's a transaction manipulation. Let's have a look at the MIPS code now, because that's something we are talking about now. Where is it? Where did it go? Sorry about that. That's okay. Doesn't matter. Back to that. Okay, so that's the one. Okay, so I've got a few of those versions I have implemented. It's a POC, by the way. It doesn't have all the features. I mean, there are a lot of ways to do the implementation. So let's go to version 1, which is a very basic version, and to the log, and just reset it. I'm going to activate the log here. All right. So just go to, sorry, that one. Okay, in that page. Okay. So that is activated. And if I just, and that MIPS code is just designed here to be executed when a page gets unloaded. So I'm going to just refresh the page. Just refresh the page. And as you can see there, DOM transaction manipulation is there. I'm not sure whether you can see that, but. And in the log file, let's have a look. Version 1. Okay. Just refresh that again. Sorry. Yep, there you go. So that is being detected here because it's not a part of the web page. Let's go to version 2, which is the salted version. So if you have a look at the code, sorry, look at the code, the salted version simply use that function instead. So it simply use the salt to make the packet different each time. So, okay, let me show you that. So that version 2 is activated now. It's activated, and just refresh the page a couple of times and see what's happened. So you see that the hash value keeps changing, right? So that's a sorted version. Okay, let's have a look at the integrity. Okay, so now we got the a sorted version, so what the attackers can do is forging the MIPS data. So if you have a look at the code just briefly there, what you do is simply rewriting the code. It simply just simulates a MIPS code here. So if I just activate that just now, sorry, yes, so that one is activated now, and just refresh the page, and let's have a look at the logs. Refresh the page, and refresh. See that? So it doesn't detect anymore because it's forged. The information that we're receiving from the web browser is just forged. So how can we detect it? So we've got the integrity check here. So just select it. Refresh a couple of times. Just make sure that it's executed. Hey, just look at that. So we've got a new field there, which is called MIPS integrity. So that is just red there because it's not the integrity value that we were expecting in that piece of code. Okay, so that's one of the things that we have implemented. What's next? Anti-rootkit. Okay, so let's activate the rootkit code here. The rootkit code is simply hooks into a couple of those functions there, and so if we simply run the code again, I think we are going to lose the detection here. You see that? It's blue now. It's blue now because the integrity looks okay. I'm sorry about that. It's just rootkit. It was not activated, sorry. Okay, just activate it again and just reload the inject, execute it, and just refresh. And still, it's blue because it is not for the rootkit. But if you activate that code, anti-rootkit code, sorry, just refresh, execute the code, and you see that new field there, DOM integrity. Well, so that actually is the field where you see the integrity of the DOM is not right. So that's the reason why it's marked red. I think we're almost out of time. I've got just one more thing to show you. It's like a script to it's just a zero knowledge protocol. And I'm going to activate the MIPS forgery inject. Just run it again a couple of times. Execute the code in it. If you have a look at the log of that, yeah. So the MIPS integrity is failed there because so essentially it's the same thing that that ZKP stuff is the same. Okay, I'm just out of time right now. So thanks a lot for your listening, and I really appreciate that.